start this next lesson, we're actually going to begin with some review. We have this function here for position, the position of an object, and I'm going to ask you to go ahead and find the average velocity from 0 to 2 seconds. Go ahead and do that real quick. Okay, so in order to find average velocity, we need to find the displacement so that we can take that displacement divided by the change in time. So between 0 and 2 seconds, 9 meters was the position at 2 seconds. At 0 seconds, the position was 1 meter. So that gives us an average velocity of 4 meters per second. Okay, so the next thing I want you to do is actually to find the instantaneous velocity at 2 seconds. Okay, so the velocity at 2 seconds would have been 18 meters per second. In order to get this, remember you had to go to this function right here, take the derivative to find the velocity function, and then substitute into there. Okay, now you might be wondering, well, how is it possible that the average velocity is only 4 meters per second, but the instantaneous velocity at 2 seconds was 18? And you might imagine that this graph could look something like this, where it's arcing up like this, and so maybe this was 0 seconds and that's 2 seconds, and so the slope here is very steep, whereas the slope between these 2 points is not as steep. We're going to go away from this problem for just a second, but we're going to come back to it in a minute, okay? So when I say the word acceleration, what do you think of? What does that make you think of? Maybe you think of a car going really fast, and that's often what we initially think of when we hear the word acceleration, because we think of cars that accelerate quickly. But acceleration is a lot more broad than that, and just because something's going fast doesn't mean it has acceleration necessarily. Okay, acceleration is about change, about changing speed. So think about when you're in a car, if you're stopping or you're at a stoplight that turned green and you push down the gas and you start to increase your speed. Those are times when you're accelerating. Just like if you're walking and you decide to stop, that's acceleration. One thing I like to say is that acceleration happens when you get that feeling in your stomach. Okay, think of the feeling you get on a roller coaster or on a swing in your stomach. That feeling is what you get when you're accelerating. And you get that feeling because all of the organs and everything inside of you is pressing together at the same time because it's experiencing that acceleration with you. So those are the times when we have acceleration, when the velocity changes. And we're going to talk about quantifying acceleration in this video. So acceleration is actually defined as a change in velocity. Okay, now this is a very simple definition, but there's something really subtle that we got to make sure we understand. Velocity is a vector, meaning it has both magnitude, if you remember, and direction. Okay, this means that you can have a change in velocity but keep the same speed. How do you think that's possible? Any situation where your direction is changing means you have acceleration. So if you're spinning in a circle, you're experiencing acceleration. Okay, and we'll get into that type of acceleration later on in the year. For now, we're going to talk about, since we're talking about one-dimensional motion, we're going to focus on one-dimensional acceleration. So the first thing I want to talk to you about is average acceleration. Okay, we can find average acceleration by finding the change in velocity and dividing it by the time that's passed. Okay, you might recognize this as the slope of your velocity graph. Okay, in addition, instantaneous acceleration, so we have the same relationship between acceleration and velocity as we did with velocity and displacement. Our instantaneous acceleration can be found by finding the rate of change of velocity. Okay? And so it's a continuation of what we've done before. Okay? So if this is a velocity graph, where we have some function going on, okay, if I want to find the average velocity between 2 points, or sorry, the average acceleration between 2 points, I would find the slope of a line connecting them, which is what you're doing right here. Okay, and if I wanted to find the instantaneous acceleration, that would be the slope of a tangent line at any point. Okay, would give us our instantaneous acceleration. Okay, alright, so I want to go back to this example right here, and I'm going to ask you to find average acceleration between 0 seconds and 2 seconds. So in order to find average acceleration, remember we said that was the change in velocity divided by the change in time. So in this case, what we're going to use, instead of using this position function to now find our acceleration, we use this velocity function. Okay, because we're looking at average change in velocity. If we substitute in 0, we get 2 meters per second. If you substitute in 2, you're going to get 18 meters per second. Okay, that's going to give us an acceleration of 8 meters per second per second. The way we interpret this is that during this region, during these 2 seconds, the velocity was increasing by 8 meters per second every second. Okay, so if at 0 seconds it was stopped, then at 1 second it would be 8, then at 2 seconds it would be 16, so that the velocity is increasing quickly. Okay, we can express this unit in another way. Okay, meters per second can actually be written also as meters per second squared. Now I'd like for you to find the acceleration, the instantaneous acceleration at 2 seconds. In order to do this, we need to find the derivative of the velocity function, okay, which is going to be, since we said a is equal to dv dt. So that would give us an acceleration function. So 2 times 9, 18t, 1 times negative 10 is minus 10. The 2 goes to 0. So we substitute in a 2 right here. 18 times 2 minus 10 going to give us 26 meters per second squared for that instantaneous acceleration. The last thing I want to look at is going to take us back to this graph that we saw before. Okay, this is a velocity graph that we saw in the last video. Alright, and we're going to do just a little bit of analysis with it. So what's going to happen here is we're going to create an acceleration graph to go with it. At what places is the acceleration 0? You should have said between 0 to 3 seconds, and then from 9 to 10 seconds. Those are the 2 places where the velocity is not changing. At what place is the acceleration negative? Hopefully you said from 5 to 7 seconds. That's when we have a negative slope. Okay, I'm going to go fairly quickly through this part. The slope from 0 to 3 seconds is 0. We have a constant velocity. Speed is not changing, so acceleration is 0. Okay, then from 3 to 5 seconds, it goes, and it increases 5 meters per second in 2 seconds, giving us an acceleration of positive 2.5 meters per second squared. Then, from 5 to 7, we go from 20 to negative 20 meters per second in 2 seconds, okay, That's an acceleration of -10 meters per second squared. Okay, and then finally, when we go from 7 to 9, that's an increase of 20 meters per second in 2 seconds. Okay, so we have a slope here of positive 10. So I think this one I did wrong. I said so 20 to -20 in 2 seconds. That should be actually -20 here, and then this one would be positive 10 right there. Okay, finally at the last stretch, we have acceleration of 0. Okay, so notice that acceleration is negative when we have negative slope, acceleration is positive when we have positive slope, and acceleration is 0 when we have no slope.